Ah oui, c'est pas... Ah oui, excusez-moi. On a trop de micros. Encore.
The pointer.
Large button here.
It's a large one, okay.
And if it doesn't, yeah.
Okay, perfect. Okay, thanks a lot. Okay, so good morning or good day. Yeah, I'm Karen Heneka. I'm a postdoc at Hamburg Observatory. And yeah, I'm very happy, and I thank the organizers to be able to present here today, in person and remote. So yeah, jumping right in on the learning from 3D tomographic 21 centimeter maps. So when I talk about 21 centimeter signal, I guess most of you know, but just to get everybody on board, this is the forbidden spin-flip transition of neutral hydrogen, with neutral hydrogen being the most abundant element in the universe. So this already sets the stage for it to be a good probe of large-scale structure of cosmology as well. So if we have here our kind of cosmic history, it's also kind of an interesting probe to kind of close this gap between the CMB at higher redshifts and I'd say in tendency lower redshift galaxy surveys that sit down here. Right? In principle, we can also measure 21 centimeter signal, we can measure neutral hydrogen, but especially the fluctuations on large scales in absorption as well as here in yellowish red and in emission against the CMB in blue here. They're a good tracer of what we call the cosmic dawn, when the first stars and galaxies switch on. So they show up in absorption, in the so-called heating epoch, as well as cosmic reionisation, where basically these first sources start to ionize more and more the neutral hydrogen around them until the signal fades down and we have the ionized universe that we observe today, or that looks like the more lower redshift one that we have for our galaxy surveys. So basically this is kind of an intensity mapping technique similar to the CMB measurements in the way we measure fluctuations. And it's not limited to the 21 centimeter line. I'm talking about the 21 centimeter line today, but it can also be other lines. You can think of, for example, optical lines, rest wavelength optical lines that redshift and, for example, at high redshift of reionisation become infrared or even far infrared lines. So there's lots of interesting things to discover at these, in this, I'd call it gap at high redshifts. So the signal is highly non-Gaussian, actually. So if we look at a non-Gaussian, this one, non-Gaussian duck here on the left, yeah. So if we randomize the phases, we had mentioned this earlier, then we get something like a Gaussianized duck. They have the same 2D power spectrum, but well, we can't really see the duck anymore. So for inference, we kind of, for a non-Gaussian signal, we kind of want to pick up also the non-Gaussian information naturally. And for detection tasks that we also have a lot in astronomy, we also want to have some representation learning so that we can detect certain types of objects. And going back to the 21 centimeter signal, the test case that we studied here and that I'm going to present in this talk is basically the inference of key cosmological and astrophysical parameters. So I have two parameters for the epoch of heating, which is the typical, the Lx here, the typical X-ray luminosity. Then we have an X-ray energy threshold for self-absorption in galaxies. We have the zeta up here, which is the ionizing efficiency, real temperature, and as a test bed, a kind of a simple test bed for cosmology, we use here the metal density omega m parameter, as well as a warm dark matter mass. And we generate light cones, which is basically 2D spatial information plus frequency dependence, creating these 3D structures that evolve in time. And we have our bare simulated ones, and we also have here what I call the optimok, an optical optimal kind of assumption for the foreground cleaning, where we assume that we can do this relatively well for surveys like the SKA, the Square Kilometre Array, and we have a more moderate assumption where much more information gets lost due to foregrounds. And well, for this inference task, lots of non-Gaussian information, we kind of naturally, and I know it's not the only way to do it, but we kind of look at networks to solve this for us. And that's kind of different philosophies one could take matching kind of the structure of the data. So the first trials that actually did this for 21 centimeter, they said, okay, well, we have this light cone down here, and we just slice it in a spatial and a frequency dimension, and we get these 2D slices. And we feed this into our networks, and we can use standard off-shelf 2D networks for this. Basically, any network that looks at image recognition as is done a lot by industry. We can also say, okay, this is a time series in the end. We have a redshift evolution, we have a time evolution. So we use, for example, an LSTM network, a long short-term memory network, which is a network that has these kind of modules that preserve time dependency, that are fed alongside each other in order to derive your parameters. And we can say, okay, we have a 3D data structure, so why not use a full 3D network or a full 3D inference? Meaning we go from a 2D kernel that convolves our image for these convolutional networks to a 3D kernel that convolves our image, which is kind of a quite natural step, I'd say. And we also found, and we tried these different architectures. And when I say we, I also want to highlight my student, Stefan Neusch, has done an amazing work here in comparing all these architectures. We found that actually, I'd say very simple, 3D architecture performs best for this type of problem with some tweaking. So there's two main tricks. So if you go from 2D to 3D, you have more parameters, so you're kind of more prone to overfitting. So what we did again, so this is a gap layer, which is a global average pooling. And we also kind of exploited that the signal in frequency is slower evolving, like in redshift, by having a filter structure where we kind of have a larger filter in redshift direction. That's made us well trainable, less parameters, but kind of matches well the structure of the data that we have. So looking at the parameter recovery for this type of networks, I have here plotted the scatter between the true labels down here and the predictions for a bunch of parameters. And we can see that we can recover jointly cosmological, cosmic dawn, and reionisation parameters quite well. We have a low scatter, and we basically don't have any bias, which is good. Except for, well, we have some regions where physically we expect to degrade in our performance, because, for example, for a very high X-ray energy threshold, basically it saturates and nothing escapes the galaxies anymore, so we're not informed anymore about this parameter. Warm dark matter turns out to be the tricky one, but this is also in line with what we find in other studies. For example, the Lyman alpha forest, where warm dark matter for higher masses becomes more and more similar to CDM, to a cold dark matter universe, and gets harder and harder to be distinguished. So we can't measure really the masses anymore that are higher. So for lower masses, we have a good recovery, but for higher warm dark matter masses, we get, well, basically cannot recover the exact mass values anymore. The nice thing here, I want to highlight here, is that even if we go to a mod-MOG scenario, which is the, as you can see by I already here, much degraded foreground scenario, when you look at the scatter plots here, this is actually plotted for different scenarios, the 3 different ones down here. So for most parameters, basically the network doesn't care if we have lots of foregrounds here or if we don't have any foregrounds or noise. So it's really good in kind of making up for that. Except for the warm dark matter case, where we're very sensitive to actually more small-scale information that completely gets washed out for mod-MOG. So this is the only case where we perform worse if we add lots of noise. And we kind of want to dive in also a little bit in the networks, and I give a glimpse of that now, to see, well, how robust are our estimates and what's actually going in there. So here on the left, I show some transfer learning where we look at basically a network that's been trained on bare simulations, no noise, no foregrounds, and been evaluated on the MOGs, and vice versa on the right side. So what we see for the astrophysical parameters, actually, for example, down here I have Lx. It doesn't matter if we train on simulations or MOGs and vice versa, we always get a good performance, and we're not getting biases. But if we, for example, look here at the omega matter parameter, what we see is for simulation-trained ones that are evaluated on the MOGs, which is basically the scenario where we train on simulations, but then we go to real observations, for example, we get a higher scatter. But if we do the vice versa one, we're like, oh, we know our noise model really well, and we now train on that, and then we go to something else, in this case, the simulations, we actually get a large bias in our parameter. So one needs to be careful. Different parameters have kind of different sensitivities and particularities here. But the nice thing is that actually the astrophysical ones, they turn out to be very robust in our modeling, in our tests. And if we look here on the right, on the top right, at gradient-based saliency maps, that's also a nice takeaway I want to highlight. We have the two slices on top, that's simulations. We have the two at the bottom, that's mocks with noise and foregrounds. We can see, so it's not that well visible, but you can see here these kind of bright areas. That's basically the areas in this light cone slice that inform most of network training. So these are impacting the most the gradient in the end, which adjusts the weights of the model. So we can see that for the simulations, the model looks at kind of the full light cone in a bit, but for the mock, it looks at more the transition areas, like when heating starts, when we go from heating to reionization, when reionization ends. And this is kind of similar to what we see also in a simple Gaussian Fisher forecast, that these transition areas, they're the most informative. So this is in a way similar for these networks. And of course, you can check your filters and, well, cross-check that they kind of look at what you think, like large transition areas and so on. Going back to the deck for a brief second, so this is just a very, very brief outlook. And we can also have these low redshift measurements where we detect sources actually, and I want to compare this. So we'll hear more about this, I think, later in the week. But just to highlight here, that's the brightest source in the development catalog for the SKA Data Challenge, the second one. And so most of the sources in this cube up here are quite challenging because they're low signal to noise, they have a small spacious size and a high level of systematics. So the little team I had a team of very young people, we were basically going a bit at it uninformed by radio astronomy, and we tried two approaches. A wavelet filtering and reconstruction, multiscale reconstruction approach that's not much tailored yet for radio sources. And we let it compete with a 3D unit that takes these sources, segments them, and then the convolution here gives us our source candidates, where we can derive the parameters. So our main takeaways, kind of our pitfalls we had in the end, was that the noise models were kind of crucial to set the choice of a training set. We had a high sparsity, and in the end, one network doesn't cut it to like a full high true positive score, so we need a multi-step or unsolvable decision on top. To wrap this up, I hope I could give you a glimpse, or at least convince you a little bit, that 3D networks, or at least for 21 centimeter light cones, are very good for 3D data of that type. And well, stay tuned, because our network, 21 centimeter PyNet, is going online soon. And I'd be really curious to try it out on other types of 3D tomographic data. And that's it. Thank you.
Thank you very much.
Are there questions? Come on, one question. You can take off your mask if you like, and then people, and say your name before.
Hi, this is Johannes Buchner. You briefly talked about what models did not work, but could you maybe just reiterate what were the aspects that didn't work, and what were the aspects that were important?
Thank you.
So yeah, so the main point about they didn't work was, well, we could also get a kind of good recovery, but the 3D CNN in the end had the best recovery values, like R-squared, scatter, bias, and so on. Also, for the 2D CNN, we lost some information, so we were not. So it looked like we can never get as good as for the 3D CNN. And the LSTM, that was a very tricky one because, well, we had always more parameters, and it was much harder to be trained. So I'd say maybe you can get at some point as good with an LSTM, but you need much more tailoring. So I think that the selling point of the 3D network is really it's so simple, and it was really easy to be trained, like in a short training time.
Okay, there's one question on Slack. Can your model recognize absorption emission lines? That's from Arthava Bagul.
Sorry, can you?
Sorry, yeah. Can your model recognize absorption emission lines?
Well, it probably could, I guess. We haven't tried it. I mean, we have absorption emission here, but we didn't try it.
It's not been trained for it, yeah.
Yeah.
Okay. So there are no more questions, then let's finish here. We have some local announcements, so thanks to all the speakers again.